Assessment 8.57 reminds us that the first step of oxymercuration was stereospecific, and yet when we discussed that reaction, we didn't talk about the stereospecificity much. Why is that? Well, let's first look at why it's stereospecific, and remember that we're going to have concerted formation of the mercurinium ion. Once we've formed that mercurinium ion, for example, on the front face, notice that both of the bonds to the mercury are coming towards you. When water attacks, and we're not going to show a full mechanism, but I'll at least sketch out this step, that when water attacks, it's going to attack from the opposite side. After a proton is lost, you'll notice that at this point in every oxymercuration reaction, the hydroxyl group and the mercury are on opposite sides of what was the original double bond. That sounds exactly like what stereospecificity would be. So why didn't that matter? Well, almost never do we isolate this as our product. We always will next cleave the mercury bond. And so that step where we add sodium borohydride to the mercurinium, or to the organomercury, when we add sodium borohydride, we remove that carbon-mercury bond, and we do it through a mechanism that is not concerted. What does that mean? It means that whatever intermediate forms, likely to be a radical, when that intermediate forms, we form the new hydrogen bond on both sides. So the memory, the stereochemical memory of this carbon-mercury bond is lost in that sodium borohydride step. What does that mean? Well, if this mercury was on the opposite side of the hydroxyl, but then when we form the new hydrogen bond, we form it on either side, there is no anti-stereochemistry anymore. The relative stereochemistry is lost, therefore the reaction is not stereospecific overall. It is stereospecific to here, but we lose that memory of the stereochemistry in that sodium borohydride reduction step.